Hi everyone, we are on our third power of a telescope, and we've been through light gathering power and the bucket and resolving power and the diffraction fringe and the interferometry. And now we're on the last power, which you probably thought was the most important power, the magnifying power. But it is not the magnifying power, and the reason is not. It is because you can't magnify what you can't see. So if we didn't get in the faint stars with the really good light gathering power, then we can't magnify them. And if we didn't resolve the binary star that looked like one star, then you can't magnify the blur. So this last power, this magnifying power, is related to focal length. We're going to explore that a little bit more precisely. What is focal length again? To review, focal length is the distance from the primary mirror, which is where the incoming light bounces off and reflects off of, that distance to the prime focus. That is known as a focal length. The distance from the primary mirror to the prime focus. Now you might say, Professor Sutar, it doesn't look like anything's happening back here because you have this secondary mirror in the way, and you would be correct. This is a Newtonian mirror configuration developed by Newton himself to improve on Galileo's refractory design. He designed the secondary mirror very close to the prime focus, which would be here. He moved the prime focus over to here, and it actually intersects with the light coming in. So it really does add a bit of power to this area where there is the prime focus. So you can see here now that there are actually two focal lengths in this telescope, in this Newtonian telescope. There is this initial focal length, and there's a focal length that is between the eyepiece and the focus right here. So there are two focal lengths here, and this comes into play when we talk about magnifying power. In fact, magnifying power, or for all you photographers out there, Fstop, something you know and love, is the quotient of the focal length to the primary focal point, the prime focus, over the focal length of the eyepiece. Both focal lengths in these telescopes with secondary mirrors. Again, you can even have tertiary mirrors. We're really working with the two mirrors here. So what you see is this. You can have one focal length between the primary lens and the primary focal point. You can have another focal length between the eyepiece and the primary focal point. They may not line up like you see here, but in dividing this longer focal length by this shorter focal length, you get the magnifying power, or the f-stop. Now, that means that, well, I guess we could change out the eyepieces, and you can change out the eyepieces. This happens to be an eyepiece which has a relatively long focal length here. It's certainly much shorter than the prime focal length, but has a relatively long focal length. A longer focal length means that your eye is farther away from that image that's posted right at the focal point. So if the image is farther away, it seems smaller. And in fact, this is a smaller image that seems farther away with this relatively long focal length at the eyepiece. But you could change that out, and you could get an eyepiece that has a relatively short focal length. And then you are not so far away from the image, so the image seems bigger. And in fact, that's the logic of this, that you are not so far away from the image so it seems bigger. To make the math fit, Think about it. If you had a focal length that was smaller for the eyepiece, you would have a smaller number in the denominator and you would have a larger number in the quotient. So you'd have a larger magnifying power. So we're all working with the inverses here. And by changing out the eyepiece to an eyepiece with a shorter focal length, you add magnifying power to your telescope. See you on the other side.